Review of electromagnetic principles, continuation. In this chapter, we will inspect electric and magnetic fields from small dipoles. These are the electric dipole and the magnetic dipole. Magnetic dipole is basically a small loop. We will introduce the concept of wave impedance and also find the expression for the maximum possible radiated field. Now take this picture on the left over here. If you want to find the radiation field from a piece of wire, this piece of wire can be component leads, or it can be a track in a printed circuit board, or it can be just a connecting wire between two circuits. So if you want to find the radiation field from such a wire, then you can divide that into very small dipoles. These dipoles are shown here. Then if you know the expression for electric and magnetic fields from a small dipole like this, then you can add up all the dipole fields from the various dipoles to find the total field. So that is the principle involved. So the basic expressions that we want to know is that from the small electric dipoles. These are called the electric dipoles. Now you can imagine another scenario in which you have a wire that is closed, like a loop like that. So here we have two possibilities. One possibility is that you can divide this wire, as we did before, into very small dipoles, find the electric and magnetic fields from each of these dipoles at a point where we are interested in finding the fields, then sum it up. Another way is that this area of the loop, that you can divide into very small loops, so that it covers more or less the complete area. Then these are called the magnetic loops or magnetic dipoles. Then you can find electric. Then from there you can find the total magnetic field. So there are two possibilities in finding the fields. Now first consider the electric dipole. So this is represented by a small piece like this, which has a dipole moment. This dipole, suppose that this is part of a wire, a small part of a wire of length small l and carrying a current I. Then the electric dipole moment is defined as m subscript E equal to I into L. So the current is directed in the z direction. So this is the Cartesian coordinate, x, y, z, what is shown. But we will find the expressions in spherical coordinate because that is more convenient for us. So the spherical coordinate is defined like this. So if this is any point in space P, then from the origin to this point, that distance is called r, that is one of the coordinate. Then from the z direction, an angle theta. So this is the second arm of the coordinate. Then the rotation phi from the x axis. So this is an orthogonal system, r, theta and phi. So P is expressed in terms of r, theta and phi, the orthogonal spherical coordinate system. Now, if that is the case, we can find the expression for the r component of E field, the theta component of the E field, and the phi component of the H field. So H will have only one component, that is phi, because if you have a current in this way, the fields are around this in the phi direction. So you have only phi component for the H field from the symmetry. Then for the E field, you have only the R component and the theta component. And you don't have any phi component for the E field. Now, if you look at the expression for the electric field and the magnetic field, Z0 is the free space impedance 377. We will not go into the details of these equations because we are interested in only one term of these equations usually. Now what you can notice is that this is varying with respect to the distance. Now it can vary as r squared or r cube, or if it is theta component, it can vary as inversely proportional to r, or inversely proportional to r squared or r cube. So here you can see that it can vary as 1 over r or 1 over r squared. So as you are moving far away from this dipole, now by the way, it is assumed that the length L of the dipole is so small compared to the distance that you are interested in the field as well as the wavelength involved. So then only these expressions are true. So this is a very small dipole compared to the wavelength as well as the distance r. Now very far away from the dipole, 1 over r cube terms and 1 over r squared terms fall off very fast, and basically the terms that are significant in value are 1 over r terms. So where are the 1 over r terms? So in this you don't have, because this is either 1 over r squared or 1 over r cube. So here you have one term that is varying as 1 over r, and here also you have one term varying as 1 over r. So these fields are more dominant far away from the dipole. So let us look at the expressions for those fields. So E theta and H phi, and they are orthogonal to each other, these two terms. And far away from the dipole, this is almost like a transverse electromagnetic wave. So the Poynting vector or the energy flow is in the r direction far away, and theta component and phi component are lying in a plane perpendicular to the direction of propagation of the fields. So this is the expression for the theta component, and this is the expression for the phi component. They are proportional to the current, and also it varies as a function of sine theta. So it is angular dependent. So when sine theta is 90 degree, the field will be maximum, and when sine theta equal to 0, in this direction the field is 0. So the radiation pattern is more like this, as I am drawing here. So this will be the radiation lobes far away. Now consider the case of magnetic loop. So here again from the symmetry, there is a loop here in the xy plane. Again spherical coordinate is defined, and this has got a dipole moment I times a, where a is the area of the loop. So the shape of the loop is not very important, even though for convenience it is shown as round. It can be any shape as long as this loop is very small compared to the wavelength and the distance where we are interested in finding the field. So the shape doesn't matter really. So this is the dipole moment. Now here also, from the symmetrical consideration, you can see that any small voltage can drive a current easily around it. So it will create magnetic field. So it can create an electric field drop around the loop. So you can see that the electric field will be in the feed direction because it can easily create an electric drop. Then the magnetic field will be in both R direction as well as theta direction. So you have three components only. Other components are zero. So here also these components can vary as 1 over R cube or 1 over R square or 1 over R. And far away, when beta R far less than 1, beta is 2 pi by lambda. So at far distances we are interested only in terms that is varying as 1 over R, because those terms will be the dominant one and others will be approaching 0. So those terms are written over here, and you can see that phi and h are orthogonal to each other, and they are also orthogonal to the direction of propagation. So far away you can assume that this produces something like a TEM wave. Now E field and H field both are proportional to the dipole moment I0 times area of the loop, and also sine theta. So here also the radiation component is, the radiation is maximum when theta equal to 90 degree in this direction, in the plane of the loop, and minimum or zero perpendicular to the loop in the z direction, far away from the field. Wave impedance. Wave impedance is defined as the ratio of electric field to magnetic field, but those components that are perpendicular to the direction of propagation. So if direction of propagation is R, away from the origin, then the electric and magnetic fields in a plane orthogonal to that direction is taken to find the wave impedance. So for the electric dipole, it becomes the ratio of the theta component of the E field to the phi component of the H field, and for the magnetic dipole it becomes the phi component of the E field and the theta component of the H field. So this wave impedance is a function of the distance or electrical distance from the dipole, and it is also dependent upon beta R. Now let us find the wave impedance of the E dipole. So if you take the expression for the theta component of E and the phi component of H that you have seen in the previous view graph, these expressions, then you can see that it can be simplified by this expression where beta equal to 2 pi by lambda and beta r equal to 2 pi r by lambda. Now if we have beta r far greater than 1 or far from the dipole, the far field condition, then this becomes very small, and basically what is in the square root is just 1. So you can see that wave impedance for electric dipole far from the dipole is nothing but the free space impedance Z0, that is 377 ohms. But situation is different when beta r is far less than 1 or near to the dipole. Then wave impedance, you can see that now beta r is small, so this becomes very big, so 1 is negligible. So simplifying, you get it as Z0 by beta r, and wave impedance is far greater than the free space impedance Z0, that is square root of mu by epsilon, or C equal to 1 by square root of mu epsilon. Now the expression for wave impedance, simplifying, you get as 1 by 2 pi f epsilon r, where epsilon is the electric permittivity. So you can see that very close to the dipole, wave impedance becomes quite big, and far from the dipole it reduces. But of course this expression is valid only very near to the dipole, beta r far greater than 1. Beyond that it is not valid. Now we can find the wave impedance for H dipole. So from the expressions for the E field and H field and the ratio of that, it can be shown that wave impedance equals Z0 multiplied by this expression, where beta equal to 2 pi by lambda, beta r equal to 2 pi r by lambda. Now here also we can take two conditions. One is when beta r is far greater than 1. So under that conditions you will see that wave impedance is nothing but the free space impedance. And when beta r is far less than 1, you will see that it is given by free space impedance multiplied by 2 pi by r by lambda. So near to the magnetic dipole, wave impedance is smaller than free space impedance, and it is given by 2 pi f mu r. Mu is the magnetic permeability. So you have two different kinds of expression near to the dipole for electric dipole and magnetic dipole, whereas far from the field, far from the dipole, both gives free space impedance. So let us plot this out. So in this wave impedance is plotted with distance from the dipole. So to normalize for the frequency or wavelength, we take beta r, 2 pi r by lambda as the x-axis. So beta r equal to 1 will be 2 pi r equal to lambda. When lambda equal to 2 pi r, then it becomes 1. And this is the wave impedance. And this blue line is for electric dipole and red line is for the magnetic dipole. You can see that for the magnetic dipole, it starts from a very low value, the impedance. Then as the distance is increased, it reaches 377. For the E dipole, it starts from a high impedance when you are very close to, then it comes down and reaches 377. So often we talk of magnetic fields. When you have a problem of magnetic fields, we talk of low impedance magnetic fields, and we often talk of high impedance electric fields when we are close to the source. So the reason for those expressions are coming from this graph. High impedance electric fields close to electric dipoles, low impedance magnetic fields close to magnetic dipoles. Far from the dipoles, wave impedance is free space impedance for air. Wave impedance concept we will be using quite extensively in the analysis of electromagnetic shielding in a later chapter. So there we will talk about why it is easier to shield against high impedance electric fields, whereas it is very difficult to shield against low impedance magnetic field, or we will say that shielding is more difficult when it is low frequency magnetic fields. Now, where will be the maximum radiated field? So this is a dipole. First we look at the far field. Maximum electric field we have seen before that when theta equal to 90 degree. So in this direction, and the expression is given by this. So the maximum radiated field is proportional to the current as well as electrical length of the dipole, L by lambda, and inversely proportional to the distance from the dipole. So this is perpendicular. Maximum radiation field is on a perpendicular plane to the dipole. Now here maximum radiation is in the plane of the loop in the far field, and the A is the area of the loop. So maximum field in the field direction is proportional to the current, inversely proportional to the distance, and ratio of the area of the loop divided by lambda square, wavelength square. Now in the near field, maximum couplings are along the dipole length and perpendicular to the loop. So this is opposite to that in the far field. So in the near field, maximum coupling is along the dipole for the electric field and perpendicular to the loop for the magnetic loop. Now this shows example calculation for the maximum radiated field at a distance of 10 meter and 10 centimeter dipole versus 3 by 2 square centimeter loop. Again, shape of the loop can be anything. So in some of the standards it has been specified that electric field should not exceed 32 microvolts per meter at 30 megahertz. So you will already exceed this limit if you have a small dipole carrying a current of 170 microampere. And if it is for this small loop, 450 microampere will be the limit. Above that, you already exceed this value, permissible value, by the government regulations. Similarly, at 230 megahertz, to reach this value, you need only 22 microamperes, and for a loop, you need only 8 microamperes. Because for the loop, it is area divided by lambda square. That is why the changes are much faster here. Now, sometimes we can find the radiated field in time domain, other than the frequency domain. Then you can see it is proportional to rate of change of current, di by dt, and the length of the dipole, and inversely proportional to the distance. And mu 0, 4 pi, these are all constant. C is also constant. You can write it in this way: 10 to the power minus 7 L by R di by dt volts per meter, and B phi flux density 10 raised to minus 7 L by CR di by dt Weber per meter squared. So you can see that the ratio of E and B, it is speed of light. Radiation field is proportional to time derivative of the current.